Okay, hello. I just wanted to show you two different methods of proof that some of you might be familiar. And if not, I'll explain those two methods. So the two methods that I'm talking about are proof by contradiction and proof by mathematical induction. So proof by contradiction, and both of these two methods make a lot of sense. So I want to show you with the two examples, one on proof by contradiction and one by proof by induction. So I'll do one example for proof by contradiction, which is essentially kind of, I'll show you essentially in two different parts. So the example is this. This is a very classical example. Show that, I'll write in two parts. The first part is there are infinitely many primes, and the second part is there are infinitely many primes of form 4k minus 1. So I want to show you how we can prove these two. Okay, so the question is asking you to show that there are infinitely many primes, and the second one is asking you that there are infinitely primes of a certain form. So what it means is it is 4 times an integer minus 1. So there are typically two ways of showing that there are infinitely many of something. One method would be to just write down a formula and say, well, here's a way to construct these infinitely many objects, in this case, prime numbers. And the second method is to say, well, let's see what happens if there are only finitely many of them, and deduce that that's impossible. So basically get a contradiction, get something that is false, and then that means that the initial assumption that there was only finitely many of that is not valid. So that's the idea of proof by contradiction. So as you know, for prime numbers, there's not really a formula that you can come up with. So it's better to assume that there are only finitely many and then get a contradiction. So assume there are only finitely many. So assume P1 all the way to Pn are all prime numbers. So your objective is, you know that, like, for example, 2 is a prime, then the second one would be 3, and so on. So let's assume there's like a finitely many. It could be 10, it could be a million, but it is, whatever it is finitely many. So the objective is to produce a new prime number. And this is a technique that probably most of you, or if not all of you, have seen this. So we're going to multiply all of these prime numbers and we're going to add 1 because we want to create something new. So if you take a look at this integer, this is more than 1. Because that integer is more than 1, it has a prime factor. So since this integer is more than 1, it has a prime factor. Now assume that prime factor is a prime factor p. So we know that all of the prime numbers are given in this list. So by assumption, this prime factor must be one of the PIs. So suppose PI divides P1 all the way to Pn plus 1. So you have a PI that divides that. But since PI also divides P1 through Pn, we must have pi divides 1, which is a contradiction. Okay, so one thing that I forgot to mention at the beginning is anytime I'm going to start a proof with a certain method, I'm going to specify. So I'm going to specify here that on the contrary, which means I'm using proof by contradiction, assume that is the case. Assume these are all of the prime numbers, and then we got a contradiction. So for the second part, we would have to essentially do the same thing. We would have to show that there are infinitely many primes, which means we would start with assuming that there's only finitely many of them, and then we get a contradiction. So how do we do that? What we are going to do is we're going to see if we can. So I'm going to use a different color, and I'm going to do basically the scratch of this. Let me keep that first. So this would be my scratch work. So this is not part of my solution, but it would be like basically finding the roadmap. So let's assume that P1 through Pn are all primes of form 4k minus 1. And let's see how we can get a contradiction. So let's just follow the same thing that we did. We have P1 through Pn plus 1. Certainly one P divides this one. One prime P divides this one. But the problem, let's think about what the problem is with that argument. That's not going to finish up the solution here, because all we are saying is that there's a prime dividing P1 through Pn plus 1. Now, could that prime be not of form 4k minus 1? Potentially. Could it be 2? Potentially, because these are all odd, and then you add 1, so that becomes even. So P could be 2. So let's find a way to avoid 2. If I want to avoid 2, I would have to make this expression here, the highlighted expression, odd. So if you have a prime number P, when you look at the prime number, it would be either 2, or it would be 4k plus 1, or it would be 4k plus 3, which is the same as 4k minus 1. Right? 4k plus 3 and 4k minus 1 are the same thing. So I want to avoid 2. I can avoid 2 by considering this number, P1 through Pn multiplied by 2 and then added 1. So we could consider that. Now, now I can make sure that P is never 2. But maybe all of the primes are of this form. So now the question is this: what if all P's are of the form 4k plus 1? Then, so what if every single prime factor of this number right here is of the form 4k plus 1? Then that means that number, then that means the 2 times P1 Pn plus 1. So when you take that mod 4, when you take the remainder, when you multiply 4k plus 1, a bunch of 4k plus 1s, you're going to get another 4k plus 1. So that would be 1 mod 4. So is that possible? Well, that is actually not possible, because that means 2 times P1 through Pn must be even, right? Which is not correct. I'm sorry, it must be a multiple of 4, but that's not correct. Okay, which is not correct. So Now that we obtained the solution, we're going to write down the solution. So this is the write-up of the solution. Okay, so what do we do as a write-up? So we're going to prove by contradiction. So on the contrary, assume P1 through Pn are all primes of form 4k minus 1. Now consider the integer, let's call that d, 2 times P1 through Pn plus 1, which is more than 1. So every prime, so let me just write it down a little bit differently. So if every prime factor of D is of form 4k plus 1, then D is going to be 1 mod 4, which is just to say the remainder is 1 when you divide by 4. And that means 2P1 through Pn is 0 mod 4, or P1 through Pn is even, which is a contradiction. Okay, so now we just showed that there is some prime factor for 2P1 through Pn plus 1 that is not 4k plus 1. So let P be a prime factor of D that is not of form 4k plus 1. So there are two possibilities. Either P is 2 or it is 4k minus 1. So since D is odd, P is not 2, since D is odd. Now, that means P must be of form 4k minus 1. Now, by assumption, P must be one of the PIs for some I. Therefore, Pi divides 2P1 through Pn plus 1. But since Pi divides 2P1 through Pn, that means it must divide 1, because it divides this expression plus 1. It divides 2P1 through Pn. We conclude that Pi divides 1, which is a contradiction. Okay, so that's the first example I wanted to do on proof by contradiction. So just notice the write-up, the distinction between the write-up of the solution and the way we obtain the solution, the scratch work. So make sure whenever you start with a proof, just put like the most important part of your proof at the beginning. So if you have, if the solution has an answer, if the question is like, find a sum, or is it true or false, whatever, something that you want to prove, some claim that you have, put it right on top. In this example, the proof was just given. The statement of the theorem, the statement of the problem was given. So what I put on top at the very first line is the method that I'm using. So on the contrary, I'm assuming this is the list of all of the primes of form 4k minus 1. And then eventually I ended up with a contradiction. So and then in between, of course, there's quite a bit more that we need to cover. But I wanted to mention these two methods. This is the first one, and I'll show you the second one in a different, different video.